Academy. Today we want to look at Stoke's theorem. Stoke's theorem is one of the integral theorem and very interesting. Remember we have looked previously Green's theorem. We have looked at the Evangel's theorem. So if you have not checked on those, kindly go back and check from the videos above. Make sure you subscribe if you have not subscribed. Make sure you also share with your friends. Again, leave a comment for any question that may arise in the tutorial or any other question which you may meet on the way on your academic areas, either in your research or in another field. So this Stoke's theorem, just to give a brief introduction about Stoke's theorem, is that Stoke's theorem is named after an Irish mathematical physicist who is called Sir John Stokes. Sir John Stokes existed between 1890 to 1903 and is actually this Irish mathematical Sir John Stokes is not the one who really discovered Stoke's theorem. And Stoke's theorem was basically discovered by a Scottish physicist called Sir William Thomson. And Sir William Watson existed between 1824 to 1907. There was a letter that he sent to Sir John Stokes in the year 1850. And in that is when Stokes learned about this theory. So this theory is very interesting and it's very key in our daily mathematical area, more so in physics. Having noted that, if you have not yet subscribed to this channel, kindly subscribe. And before we look at what really Stoke's theorem states and how we deal with it. Okay. So sometimes we say that Stoke's theorem is actually a higher dimension of functions of Green's theorem. And we tackled Green's theorem in the previous tutorials. So if you have not looked at them, kindly check. So it states that if S is an open two-sided surface bordered by a closed non-intersecting curve C, which is a simple closed curve, then and if A has a continuous derivatives, these are continuous derivatives, then this will be true. This is actually the curl of A. The curl of A against the surface ds, and if this is dot ds, will be equivalent to the closed surface of this, where n is a positive outward normal. So this is basically a breakdown of what we say, that the line integral around a given boundary curve of S of a tangential component of f, where f is actually a given vector, is equal to the surface integral of the normal component of the curl of f. So this ideally means same. So we are talking about the curl given a surface integral, and this is the curl of f. Remember, in between here we have dot multiplication of ds. So this is equal to the surface against the projection of the surface of the vector f dot dr. So they relate that way. But keen to note is that this surface should be a positively oriented. It's a positively oriented. What we call a counterclockwise acceleration. So that every time you are moving along the surface, you'll find that your left hand is pointing or the direction of the surface. while moving, and n is now the outward normal is upwards to your end, is pointing to the direction of the hand. So if the circulation of f, which is the vector defined this one around C of any oriented surface S, is the direction counterclockwise, that's key to note, in respect to surface unit vector n equals to the vector n equals to the curl of f, integral of curl of f dot n ds of s, which is what we are talking about here. So here there is basically a dot of that, and this is dot of that. So that's the dot operation. So having noted that, it will mean that if we are talking about a given field, just have a sketch here of what we expect. So this is y-axis, this is x-axis, this is z-axis. So if we are having a given surface here, it's a continuous surface, and you find this is now our C, then our n is basically upside like that. So that if you do counterclockwise, that's the moment we are calling counterclockwise, it will mean that the surface, which is this one, that surface is basically up towards moving along the surface, is actually the surface is always in your left, it's always in the left, using the counter what we call counter clockwise circulation. It will mean that if you let a given S, which is this, to be an oriented piecewise smooth surface bordered by a simple closed piecewise smooth border curve C, as I've just demonstrated here, with a positive orientation, and F being a vector field whose components have continuous partial derivatives on the open region in the surface, then it will contain the surface which contains in S. Then this relationship here will hold. It will be true. Okay, so having noted that, we can try to verify whether this relationship owns in this equation. So that if it owns, then it will be a sure way of showing that Stokes, what we have just mentioned about Stokes theorem is true. So remember, where do we apply this idea of Stokes theorem in our daily lives? We normally apply this idea in a concept in physics we call electromagnetism. So in electromagnetics is actually the idea of this, because we are actually doing a declaration about the intersection of differential forms of manifolds, because these are manifolds, and line integral in this case will be latent to the surface integral of a vector field. And if you compare these vector fields equivalent to what we meet in electromagnetism in physics. So this is a sure way on how we apply this. Now let's do the working of this. We know that the relationship between here, we know we need to get the surface f dot dr, okay, being equal to the surface integral of the curl of f d theta. Okay, so we know we can first start from the sure sign. We can start with the sure sign. We can start with this sign, and then afterwards we work on this. So if you are working about on of S, say that is C of F dr, because this is the dr, and I know that our R given in the equation given here, our R is basically if you look at the F given, our F given is y high minus xj. So that tells us that from our polar coordinates, if F is given by y I minus xj, and we know that y is given by r using polar coordinates, r sine say t, okay, sine t, and x is same as r cos t. Then it will mean that r can be given as r cos so this is r cos because you are looking about F, so r given by r cos t I plus r sine tj. So you have that relationship there. So that this will mean that our F now in this, remember from what you are given here, we have the circle, which is x squared plus y squared equal to 9. This indicates that r is actually 3. So that our F in this case can be written as 3, r is 3 sine t, or you can call it sine theta depending on what you are operating with. Take away 3 cos tj. Okay, so that if this is our r, then I can get the dr. So dr will be equal to if we divide this sine, you are going to get cos, so 3 cos t, okay, take away there is I there, so take away which becomes positive, of course this one becomes positive, 3 sine tj. So that if I do f dr, I do f times is partial dot is partial, I'm basically doing f, we know f is this times this. So what am I getting? You'll see that this gives you -9 sine squared t. It's a dot relationship. So if you multiply and that, you get you don't get a vector. Okay, so take away 9 cos squared t. Cos squared t. This means that this, like if you factor out 9, this will be sine squared t plus cos squared t, which is basically an identity, which is 1, and therefore we are getting -9. So literally what we are saying is that f dot dr is actually -9. But if we get the integral of the curve, remember the curve is running from 0 to 2 pi because the projection is a circle. The projection is a circle. D theta on d theta, you can use d theta here on dt, whichever case. So this will be -9, and this becomes 2 pi minus, or take away 0, which is actually that. So you are going to get -18 pi. So that is the left hand side of the Stokes theorem is actually -18 pi. Next, because the question is verify the Stokes theorem of that hemisphere, then what we are doing here is we work on the curl of f. So the curl of f is basically defined as the determinant or the absolute of that of I, j, and k. Okay, you arrange them in that form, then partials dx, partial dy, partial dz. Okay, and down here what we are having is actually for f I is y, j as -x, and k as 0. So if you work out this, like working for the determinants of this, you will get -2k. You get -2k. You basically get -2k. So you are getting -2k. Okay. So that now, if we do this dot ds, so you find that our dot ds is to give you exactly 2. So now that we have this one, this will be running from 0 to 2 pi because of the projection of x, and then this will be is r. So r is 0 to the maximum of r is 3, the radius. Then this is -2 k dot dr ds, but in reducing the dA is actually dr d theta. Okay, dr and d theta, because of the arrangement of these r first. So if you work out this, you are basically getting -2. Okay, it's all signed. Then I can see the first thing is r squared over 2 for dr, of course running from 0 to 3, and whichever you get here you do 0 to 2 pi. Okay, d theta. Okay, so that now in this, now you can see that comes 4.5, or 4.5. So what I'm having here is having 4.5 by 2, so I'm getting -9 from 0 to 2 pi to 2 pi, okay, and d theta. Okay, so this one, it will mean that you have negative 9 theta for 0 to 2 pi. So if you substitute this, you'll get that this is negative 9 times 2 pi, which is basically negative 18 pi. Remember, this negative 18 pi is actually what we had gotten in the left hand side, and it's the same that you have gotten when you have used applying the Stokes in the sign of curl. Remember, if you have not subscribed to this channel, kindly subscribe. Make sure you share with your friends. And again, if you have any question, kindly feel free to leave the comments below, and also subscribe and share with your friends. So that is Stokes theorem. Until next time.